Hi, I'm Bob Pryor. I'm talking to you today about solving trigonometric equations. We're going to start off simple with some very simple equations and work our way up. So we're going to start with kind of an introduction to what happens when we find values of x or theta when we have some given restrictions, such as in part A, find theta when the sine of theta is square root of 3 over 2 and theta is in quadrant 2. First of all, we know that sine of theta is square root of 3 over 2 at 60 degrees. So we can say that theta hat is 60 degrees. In quadrant 2, that means 120 degrees. So theta equals 120 degrees. In example B, cotangent of x is negative square root of 3 over 3. This time the restriction is that x is between pi and 2 pi. That means we're talking about radians. Now that means from pi to 2 pi, that's quadrants 3 and 4. And the fact that cotangent is negative, that means we're in quadrant 4. For cotangent to be radical 3 over 3, that's where theta hat is 60 degrees, or in radians, pi over 3. So in quadrant 4, our answer is x equals 5 pi over 3. Now let's look at an example that has a restricted interval, and you can see here from 0 degrees to 360 degrees. Really, that's one full unit circle, and I call this the solving interval. So we're trying to find values of theta where sine of theta is negative square root of 2 over 2. That means that we're either in quadrant 3 or 4 for sine to be negative. And to be radical 2 over 2 means that theta hat is 45 degrees. So in quadrants 3 and 4, we're talking about theta values of 225 degrees and 315 degrees. Those are the solutions. In this next example, our solving interval is from 0 to 2 pi. Again, one full unit circle, but we're talking about radians this time. Tangent of x being equal to 0, that occurs at 0 and at pi. Oh yes, also at 2 pi. So we can say that x is 0 and pi and 2 pi. Except, notice that, well, x is less than 2 pi, not equal to 2 pi. So we actually can't consider 2 pi as one of the solutions. So really we have only two solutions, 0 and pi. In this equation, secant of x equals negative 2. Secant is negative in quadrants 2 and 3, and secant is a 2 at 60 degrees, or pi over 3, so theta hat is pi over 3. But in quadrants 2 and 3, those values are 2 pi over 3 and 4 pi over 3. X equals 2 pi over 3, 4 pi over 3. This time, we're going to double the solving interval. We're going to have theta go from 0 degrees to 720 degrees. This means we go around the circle twice. So we're going to look for values of cotangent of theta, where it's equal to negative 1, and cotangent is negative in quadrants 2 and 4. And theta hat is 45 degrees. Well, we're going to go around the unit circle once to find the first two values of theta. That's 135 degrees and 315 degrees. But then we're going to go around a second time. And this means we're going to add 360 degrees to those values. 495 degrees and 360 plus 315 is 675 degrees. So we have 4 solutions in all, and we write them all down. Theta equals 135 degrees, 315 degrees, 495 degrees, and 675 degrees. So we got 2 values in quadrant 2 and 2 solutions from quadrant 4. In our next example, again, we're going around the unit circle twice, this time in radians, from 0 to 4 pi. Cosine x equals -1 at pi, and that's just going once around the unit circle. The second time around the unit circle, we add 2 pi, and we get pi and 3 pi as 2 solutions. Sometimes an equation has no restriction at all, and that's the case for this example. So that means that we're going to look for all possible degree values. Sine of theta equals 1 occurs at 90 degrees. And we can go around the unit circle once to get 90 degrees, but then we have seen that we can go around a second time and get another solution. In this case, 90 plus 360 is 450. We can go around again to get 360 more degrees at 810. What we're finding are coterminal values for 90 degrees. We can even go in the negative direction by subtracting 360. And we'll subtract that from 90 degrees. We get negative 270 degrees. If we go in the negative direction a second time, we're now at negative 630 degrees. And we can keep going on and on and on. So if we started making a list of all the solutions we have here, you can see already that we've got 5 solutions, and we don't want to have to do that. So what we have is a way to abbreviate this whole solution set, and that is by writing theta equals 90 degrees plus 360 degrees k. And the value of k is an integer. You know, that's positive -1, positive -2, 0. We say that k is an element of z. We use z to represent integers because the German word for number is Zahl, and so that's why z was chosen. So let's take a look at this formula that we just developed. Theta equals 90 degrees plus 360 degrees k, meaning times k. The point is that k can be any integer. K can be 0, and when k is 0, we put it into the formula. And you can see that we end up with theta equals 90 degrees. When k is 1, we put that in for k. 90 degrees plus 360 degrees. Theta equals 450 degrees. That was another one of our solutions. And we can do it for k equals 2. I'm going a little more quickly now. We can use k equals -1, k equals -2. We can pick any value of k and generate that whole set of solutions. So basically, theta equals 90 degrees plus 360 degrees k is a formula, and it generates all those solutions. So here in this next example, I'm going to solve for all. That's the clue that tells us we're going to be using plus something k. This time, though, it's radians. Let's see how that works out. Cosine of x is 1/2, and cosine is positive in quadrants 1 and 4. And cosine is 1/2 at 60 degrees, or pi over 3. And so we have pi over 3 in quadrant 1 and 5 pi over 3 in quadrant 4. Now we don't need to go around a second time, but if we did, we would generate another quadrant 1 value and another quadrant 4 value. We do around one more time and we get quadrant 1 value, again another quadrant 4 value. We can do this over and over and over again, but it's much easier if we simply write the formula x equals pi over 3 plus 2 pi k. Last time it was 360 degrees k. This time in radians it's plus 2 pi k. And you can see that we do the same thing for x equals 5 pi over 3. Together, k is an element of z, means k is any integer. Let's solve for all possible degree values of theta when secant theta is negative square root of 2. Secant is negative in quadrants 2 and 3, and it's square root of 2 at 45 degrees. So our angle measures here are 135 degrees and 225 degrees. But because we have no restriction, we're going to write both solutions separately as plus 360 degrees k. So 135 plus 360 degrees k. And then theta is also 225 degrees plus 360 degrees k. And together, k is an element of z. All right, now we're going to take a look at an example where we actually only need to add pi k, or 180 degrees k. Now I'm going to start with part B of this, with degrees. And we're trying to find where cotangent of theta is equal to 0. Now cotangent, of course, is cosine over sine, and for the fraction to be 0 means 0 over either positive 1 or negative 1. And that occurs on the y-axis at 90 degrees and at 270 degrees. So theta can equal 90 degrees plus 360 degrees k. Theta equals 270 degrees plus 360 degrees k. And k is an element of z. However, in this particular case, notice that these solutions are 180 degrees apart. 90 plus 180 gets us to 270, and if we add 180 again, we get back to the location of 90 degrees. So we can actually abbreviate this as theta equals 90 degrees plus 180 degrees k. Again, k is an element of z. Now, both solutions are fine, but it's nice to know that we can abbreviate them. Now let's do the same thing for radians, where tangent of x is the square root of 3 over 3. And being positive, that's quadrants 1 and 3 for tangent. And theta hat is 30 degrees, or pi over 6. So pi over 6 in quadrant 1 and 7 pi over 6 in quadrant 3. So again, we can, finding all possible radian values, write each one separately. Pi over 6 plus 2 pi k. 7 pi over 6 plus 2 pi k. K is an element of z. But because these values, pi over 6 and 7 pi over 6, are on opposite ends of a diameter, they're 180 degrees apart, or we could say they're pi radians apart, we can abbreviate this solution set as x equals just pi over 6 plus pi k. K is an element of z. Again, both techniques are valid, so both solution sets work, but it's nice to be able to abbreviate whenever possible. All right. So in this next example, we're going to start solving trig equations that are a little bit more involved. You'll see exactly what I mean.